So, let us start with the continue with the design of columns. Last class we have done that axially loaded column, and we have axial uniaxial bending as well as biaxial bending. But today we shall start with that one problem, example problem. We shall start with one example problem on axially loaded column. So, let us take one example, design an axially loaded tied column pinned at both ends. So, this one will give us the effective length with an unsupported length of 3.5 meter for carrying characteristics load of 1500 kilonewton and concrete grade M20, steel grade Fe415. Please note the characteristics load of 1500 kilonewton. So, what about the design load? And this is axially loaded column, design load which is Pu, we shall take it as say 1.5 times the characteristics load unless otherwise specified. So, it will be different for different cases, seismic load, wind load, like that, but anyway if it is not specified anything. So, we shall assume 1.5, which comes as 2200 500 kilonewton. What about the effective length? Effective length, say LE will be equal to same as the unsupported length, because it is pinned. So, it is pinned condition. Okay. So, for this case we have 3.5 meter. What we have to do? We have to assume a section. We have to assume a section. We can, and how shall we, what is the guideline? The guideline is that L by D less than 12, because we are considering it as a short column. Since it is a short column, so L by D less than 12. So, if L by D equal to say 12, D will be equal to L by 12 equal to 3500 divided by 12, which comes as 291.6 millimeter. So, we can assume size of the column 291.6. Why shall I go 325 or 350? For the time being, let us start that assume size of column 300 by 300. Okay. What about the E mean? As per the code, eccentricity minimum L by 500 plus D by 30, which comes as 3500 divided by 500 plus 300 by 30, which comes as say 17, less than here 20 millimeter. And let us check the slenderness. Obviously, it will be less than 12. So, we can check it. L E by D equal to 3500 by 300, which comes as 11.66 less than 12. So, this is your short column, eccentricity also less than 20, and we have so far we have assumed that 300 by 300, but we do not know that whether 300 is sufficient from the strength point of view. We are talking, this is the preliminary design, that we are getting this dimension 300 by 300 on the basis of that we would like to make it a short column. So, for that we have taken 300 300, but so far we do not know whether that your 2250 kilonewton the design load which is applied here, whether this section is sufficient, that we do not know. So, let us continue, we can find out the design load. Compute area of steel. Instead of that, what we shall do? Compute area of steel. So, PU as per the code, PU equal to 0.4 FCK AC plus 0.67 FY area of steel. Let us write down PU design load AC area of concrete AS area of steel FCK, that I can say characteristics value of concrete FY for steel. So, we can now find out what about the AC. AC equal to, so AC we can find out so we can write down here 0.4 FCK is 20, then AC will be equal to 300 square minus AS, because we are taking only concrete part, 300 square minus AS plus 0.67 times 415 times AS should be equal to 2250 into 10 to the 3, let us make it everything in Newton. So, we can get this part minus 8 AS 0.4 into 20 plus this part is coming as 278.05 AS will be equal to 2250 into 10 to the power 3 minus 8 into 300 square. I am taking this side, or 270.05 AS equals 15300. So, this is the thing, or AS area of steel will be equal to 5665.61 millimeter square. Let us say 5665. What about the percentage of steel P? That we have to check it. Equal to, say, let us say 5665 only, okay, divided by 300 into 300 into 100, which comes as 6.29%. This comes as 6.29%, greater than 6%. So, this section is not, we cannot provide this section, because the area of steel is coming greater than 6%. So, we cannot provide this section. So, that means here that we have started with that short column with the criteria that it should be less than 12. Even then you have to come to that here that you from the strength the load you have to bear, the column has to bear. So, with that 300 by 300 that steel is coming more. If steel is coming more, let us say 6.29% 5665, what is the what difficulty we can face? Even if we provide that one, say, let us find out the area of steel is 5665 say millimeter square. Let us consider 25 torr bar. Let us provide 25 torr bar. So, area of steel of each bar or AS bar I can say that is coming as, which comes as 491 square millimeter. So, number of bars required 5665 by 491, which comes as 11.53. So, we have to provide 12 numbers 25 torr. It means this is a section, this is 300, one, 2, 3, 4 corner, 5, 6, 7, 8, 9, 10, 11, 12. So, each side 2 more. So, what is the spacing here then we are getting? The spacing we shall get it here, the cover, clear cover for columns it is 40 millimeter. Clear cover is 40 millimeter for columns. So, from both sides 300 minus 40 which comes as 220 millimeter. Okay. So, 220 minus 25 by 2 minus 25 by 2, it means from both sides, from the center I am talking. So, what we are getting it here, because this is the, let us see that how much gap we have. So, if we have say 12 bars uniformly distributed, after all it is an axially loaded column. So, we can distribute that one uniformly. So, this distance center to center of outer bars equal to 300 minus 40 is the clear cover, minus 40 is the clear cover other side, minus 25 by 2 minus 25 by 2, which comes as, so 80 plus 25 105, so 195. There are how many gaps? 1, 2, 3. So, 3 gaps are there. Let us find out. So, 195 by 3, the center to center gap 195 by 3, which comes as 65, the center to center gap of between these two bars. So, clear gap between two bars will be equal to 65 minus 25 by 2 minus 25 by 2, which comes as 40 millimeter. Now, the question is here, this is say 40 millimeter. Let us say that your aggregate say aggregate maximum aggregate dimension, that is your say 20 millimeter coarse aggregate. So, that means it can come. Now, the question is coming, what about the lapping? Because we shall not get the bar from the bottom to the top, we shall not get that bar, that one single bar having that sufficient length, maybe say 1, 2 stories, 3 stories or 5 storied, we shall not get that long bar. So, we will get say maybe say 5 meter or maybe say 10 meter or whatever it is. So, if we get that one, that means we have to give lapping of bars required. So, it means even if I say that 50% of the bar will be staggered, that all the we shall start such a way that all the bars will not curtail in the same position. That means they say all 12 bars are going up and then you are at this level, and then again you are putting another. I do not want that, and that is not a good solution. So, it is not desirable, because then the section will be weak. It will be that and it will be that one say that crowded with so many bars. So, even if we say that 6 bars will be there, even then that increase in the your percentage still will be, here we are getting 6 point certain percentage. I am not talking with the code provision. So, 6.29%. So, it will be 9% then, because 50% of that also will be there. That means, if there are 12 bars, so I mean to say 12 into 491 divided by 300 into 300 times 100. This is the percentage of steel provided in this case. So, it comes 12 into 491 divided by 300 divided by 300 into 1. So, even then we are getting say 6.54%. So, when we are providing the lap, that means it should be 12 bars plus 6 bars in a particular section. That means the side by side. So, side by side, if I take it, because this is very important, otherwise that cracks, lot of other problem will arise. That is why that detailing, reinforcement, all those things is very important. So, what we shall do, we can start even if I take 50% at a particular section. Let us say we are having this bar and this bar say. So, I can provide the 1 bar here, then I can provide say 1 bar here. Similarly, I can have say 1 bar here, I can have say 1 bar here, like that it will go. Similarly, I can have say 1 bar here and 1 bar here. That means, in a particular section, because these bars are lapped, you are giving the lapping these bars. So, that means, here at a particular section you are having 18 bars. So, if you have 18 bars, 18 into 491, so the percentage of steel becomes at the lapped section, where you are providing the lapping for 50%, let us be specific, 50% of the bars, we are getting here .82%. So, it will be very difficult to do the concreting, and then if there is a void in between the coarse aggregates, if there is a void, obviously you will not achieve the concrete strength. So, that is why it is very important to use, that is why the code says that you should not use more than 6%, but even if you use say 6%, because you have to provide the lapping. So, that means, in that case I can say it is better, the designer, we should always prefer that it should not be more than 3%. If it is 3%, then whatever, even somebody uses the lapping, all the lapping in one section, even then also we shall not go beyond 6%. So, that we do not, though we write down specifically that only 50% of the lapping will be done at a particular section, but even then we shall not take any chance. So, it is preferable that your percent of steel should be within 3%. That should be the, or rather sometimes we say within 4%, sometimes we make it like that. Okay. So, let us take the section then, assume the column section as 375 by 375. Okay. We shall take that column section as 375 by 375. So, what we can do it here, E mean that L by 500 plus 375 by 30, which comes as 7 plus 12.5 equal to 19.5 less than 20 millimeter. What about the area of steel? We can take it as same formula 0.4 FCK AC plus 0.67 FY AS equal to 2250 into 10 to the power 3 or 0.4 times 20 times 375 square minus AS plus 0.67 times 415 times AS equal to 2250 into 10 to the power 3 or minus 8 AS plus 278.05 AS equal to 2250 into 10 to the power 3 minus or 270.05 AS equal to 1125000. Therefore, AS equal to 4165 square millimeter. So, your AS area of steel we have got it as 4165 square millimeter if we have that section 375 by 375. What about the percentage of steel? We can find out the percentage of steel. P equal to 4165 into 100 by 375 into 375 equal to 2.96%. So, we can get 2.96% we can get. Number of bars, use 25 torr, number of bars equal to 4165 by 491. So, that is the area for the 25 millimeter bar, which comes at 8.48. What we can do? We can provide 10 numbers of 25 torr. So, area of steel provided equal to 10 into 491 into 100 by 375 into 375, which comes as 3.49%. Even then, though it says that it should be less than 4%, because 4% means 4 plus half of that 2. So, it goes 6%, that 50% lapping. So, in this case it is all right, but even then I prefer less than 3%, and it is a designer's choice. So, you will find out in reinforced concrete design or steel design, you will find out it is something like that. You are say different school of thought, different philosophy. You cannot say this is wrong, you cannot say that is wrong. Only thing I can say that it is an idea, that it is the philosophy from where you have learned. It is also sometimes it happens in the institute itself. So, with whom you have learned that one teacher, so that way also it goes. Similarly, in the industry also with whom you have worked, so that philosophy, that actually you follow that particular one, that is the idea. So, I prefer less than 3%. So, that is the idea I usually do it. So, now, so we can say 10 numbers of 25 torr. So, what about the that say cross section? The cross section I shall provide here, always 4 corners we can provide here. So, 6, then we can provide here 2. So, we are having, though it is not symmetric, but anyway we are having say 10 numbers of bars. Now we have to provide the tie bars, sorry, we have to provide the tie bars. So, if we have to provide the tie bars, diameter 25 by 4. So, we can provide use 8 mm dia bar. What about the spacing? This will not be less than spacing number 1, the dimension of column, say 375 millimeter in this case. Number 2, 16 times the longitudinal bar, 16 times the longitudinal bar, 400 millimeter. Number 3, our code says 300 millimeter. So, we can provide 8 TOR at the rate of say 300 millimeter center to center. So, this is the one we can provide for tie bars. So, this is your that column design for axially loaded column. Okay. But here this is not the end of the column design, because it is not so simple that we can have eccentricity or we can have that moment developed. So, there are two possible cases. So, we would like to now do design of columns having axial load and moment. The moment could be uniaxial or biaxial. If this is a beam, this is a beam say, and here is a column. If the span is equal, loading is equal, I can say that this side there is no moment, about this one there is no moment, whereas about this axis there is a moment applied. In addition to the axial load, the moment is also here. In this context, I think I can tell you that if there is a frame here, the plan, I am drawing a plan here. If the columns are rectangular, this is your column. What is the orientation of the column then with respect to this? The orientation of that one, because if we take this whole building, a rectangular building type, say plan is rectangular. So, in that case obviously we can say it is easier to bend. Let us say this is a building, it is a rectangular one, that cross section, that plan, there are so many rooms. So, obviously I can say it is easier to bend along this, about say along this way, but whereas I cannot bend this way, I do, but it is difficult. If you say wind load or say earthquake load, that due to ground motion it moves like that. So, obviously it will vibrate, you can see that it is vibrating like this, rather it is vibrating like this. So, if you note this one, if you observe this, so if rectangular columns, if the column is square, there is no problem. If the column is you would say circular, then there is no problem, there is no orientation problem. But if the column is rectangular, the question is whether shall we provide the column this way or shall we provide the column this way? Obviously, we shall provide the column this way, because the where the moment of the second moment of area less, to resist that one we shall provide the column in this direction, not the other way, because here the bending, not only axial load, but bending also there. Sometimes it happens that we know we can find out, there are few cases, say for example here these corner columns, it ends here, that means here that moment could be about both sides, both axes. This column the moment will be about one axis, whereas this column moment will be about the other axis, whereas these middle columns you can say almost it is axially loaded. You may have, due to say your change in span or loading, may happen that there is a that moment developed, but in most of the cases you can find out that these columns are axially loaded, whereas these columns are axially loaded as well as bending about both axes. This bending about one axis, whereas this and this bending about say other axis. So that means we have two more cases, one is called uniaxial bending and the other is called biaxial bending. So now if we consider here that uniaxial bending and we have biaxial bending, how many cases we have? That loading, depending on the loading, number one, they are loading, what are the loading? We have PU and MU, say MU is the moment, ultimate moment, PU is the design axial load. So if we have to design this, for this we have to provide a section. One case we can have MU equal to 0, that means axially loaded. Number 2, it can happen that PU equal to 0, that means it is nothing but pure bending, that means it is nothing but that bending, that your beam problem, you can say it is nothing but a W reinforced section. And number 3, both PU and MU are present. Our code says if it is axially loaded, the strain is 0.002, the strain is 0.002. If it is say that if there is a bending, in that case what we shall say, that our code says that in the maximum stressed in the compression side, there the strain will be equal to epsilon c will be equal to 0.0035 minus 0.75 times epsilon say dash c. I mean to say, if this is the section, then we can find out this is 0.0035, this is D, somewhere here we are having the pivot, that is 0.002. So I can say this 0.0035 is a total, 0.0035 minus this is epsilon dash c minus 3/4 of epsilon dash c will give me this one. So this value will be 0.0035 minus 3/4 or epsilon dash c, or nothing but 0.75 f dash c. This curve is required to find out the strain as well as to find out the stress. So we can find out the strain and then we can find out the stress. What we do here, because it is a very say for example PU and MU is given. Now what should be the percentage of steel, that we do not know. So, what value of pu and what value of mu, that means if pu more, it does not mean that pu and mu there is no linear relationship. The relation, so that means you have to do certain kind of trial and error, and we have to find out at what percentage of steel both pu and mu satisfied, for what percent of steel and what section. Say if I take a certain section 300 by 300, and for that section if we start, then we have to find out, and let us take say 1% or 1% percentage of steel. For that we can find out, we can use this formula, we can find out the strain and all those things, and then we can get the pu and mu, and then we can say okay, it is perfectly all right. That is the thing we generally do it. But here what we generally do, that is called interaction curve, P versus M interaction curve. So, that one you can get it, I shall show you. No, I think okay, anyway. So, just to tell you, actually I have already referred this one, that design aids for reinforced concrete to IS 45, this is 1978 of course, this is SP 16, the special publication SP 16, where you will find out lot of charts and tables, all those things you can find out. Even nowadays one can write a simple small program and he can generate all those things. For each and of a table, all those things one can generate that one with that, you say one small program, it is not a very big one. So, what we shall do it here, what I like to show, I shall come in detail, that what I am talking. Let us take, I think we can show you this one, any one of them. Okay. So, we have like this, these are the chart. Okay. What we can do, and let me see whether it is available here, one sec, I can do it. I think it may be better, right? Okay. So, the same thing, it is now available in our library also online. So, you can see the same thing now available here. This is called interaction curve. What we do, this is say there is one chart, just to tell you, I shall show you how to make it also, that I shall tell you in later class. So, here what happened here, this particular one, this is for FY say 415. What we do it, we make it here, here we write down PU by FCK BD. PU is the design load, axial load, FCK BD, and mu by FCK BD square. This is for a certain percentage of steel. I can get different curve for different percentage of steel. What about this point? Because there are few salient points. This point axially loaded. There is certain point here that balanced. This point no axial load. This side is compression zone, and this portion is tension zone. So, depending on the neutral axis position, we can find out. There is one case say you are axially loaded, that means it is uniformly distributed at 0.002, the strain is 0.002. Then we have one case where there is no axial load, that means it is a simply a beam problem and neutral axis is within the section. Somewhere we are having the balance section, then we are having say sometimes say your tension zone. Finally, the neutral axis is going out of the section and where we are getting purely compression zone. That means that there even the distribution of that one say here, it may be something like this, the strain, this it can go something like this. So, what we can do, we are starting somewhere here like this, 0.002 is the strain, then somewhere you are getting 0.0035 minus 3/4 of this side. So, like that it will go. So, this is your that interaction curve. This SP16 it provides you these so many curves. So, what we can do, depending on the these charts, depending on the d dash by d means that clear that effective cover. So, what we do here, it says what it does. So, d dash means equal to 40 millimeter plus 5/2, diameter of the bar 5/2. So, d dash by d, depending on different d dash by d, we can get different strain, that is why we are having different d dash by d. It starts with 0.05, 0.1, 0.15, 0.2. So, we can have different charts. This is chart 31 for FY 415 d dash by d like that. Then we can have the other one, d dash by d 0.1, this is for 0.15 and this is for 0.2. Okay. What we can do, let me show you what we shall do. So, let us take a particular chart. It depends on that it is for a mild steel. This is for FY 250 means mild steel, but we have to go say, since we are using say Fe 415, so we have to use say Fe 415. What we shall do it here, I think I can, yes, what we can do it here, okay, one sec. Okay. So, this is the case. I can show you one example, then it will be clear what we are going to do. What we shall do, let us take PU, let us take PU say 1500 kilonewton, okay, and MU say 100 kilonewton meter. Okay. We are getting this value, and let us assume the section, column section say 350 by 350, FCK 20 Newton per square millimeter, Fy 415 Newton per square millimeter. D dash, let us take D dash here 40 plus 20 by 2, 20 millimeters say I am taking, so 50. Okay. So, we are getting this one say your 50. So, what about d dash by d? D dash by d will be 50 by 350. So, we can get so 0.1428. D dash by d 0.1428. What we can do, though it is not correct, we can interpolate of course, but we can take the table or chart, this chart, because this is, it says d dash by d equal to 0.15. What we should do, we can take d dash by d for 0.1 and also we can take d dash by d for 0.15. Here I am getting 0.1428, which is coming closer to 0.15. So, we can, so let us assume that we shall take this one, but actually we should interpolate between these two charts. What we shall do it here? So, d dash by d 0.15, this is the section, it is uniaxial, that means about this line, about this axis that moment applied. Since the moment is applied about this axis, that so I am providing the reinforcement about this. The thing is that here this is your section, moment is applied about this axis. So, we have to provide the reinforcement along this, then only we shall get the maximum benefit. We shall get the maximum, because then only we shall get the maximum benefit, because it should be as far as possible, it will be far away from the neutral axis. So, instead of providing here, we provide like this for uniaxial bending. We are talking uniaxial bending. That means the bars can be provided along these two lines. Is it clear? We are having say moment Pu and Mu. When we are having Pu and Mu, if we do not want to provide the reinforcement uniformly distributed in all four sides, instead of that, I would like to get the maximum benefit. What I am interested here, what I am interested here, we can provide the reinforcement along these two axes only, two sides only, because this one, whatever moment will be produced due to this, wherever you provide the reinforcement, it does not matter if it is actually loaded. But when you are talking say moment, so these bars if you provide say far away from this one, then it will take the maximum moment, and that is why we are providing that in two sides only we are providing reinforcement. Okay. But if it is biaxial bending, then we have to provide in all four sides. So, what we can do, if you have d dash by d equal to 0.1428, I can take this section and I can take the, I think what I can do instead of going to computation, what I shall do here, say this is your that section, what I can do, if the reinforcement, oh no, I think it is not working. Okay. No. Anyway, what I can show you, if the okay. So, this is your mu by FCK BD square. What I shall do, I shall take along this line, this is one axis which I shall get it mu by FCK BD square. Mu by FCK BD square I shall get along this, and Pu by FCK BD I shall get along this. So, I shall get a point. So, I shall get one line, and from there what are these? These are for different value of P by FCK. This is for different value of P by FCK, and then we can find out the, we can calculate the percentage of steel. So, I think I shall do it in the next class, I shall do it that with that example, the specific example how we can do it that one, okay. And if it is possible, if it time permits, then I shall show you with that example of say how to make it in the computer, because that one it is very simple one, it is not a very difficult problem. One can do it because all the charts, everything one can simply make it on his own, all those things you can make it, okay. So, let us finish it today. Thank you.